Okay, so good morning to all. In our previous class, let me share this screen first. We discussed about whatever we completed in our, previous week, what all we covered in the previous week. So, because of short of time, I forgot to take the questions. But if you have any questions with respect to the previous lecture that we had, which was a revision for the complete week. So, with respect to that, if you have any query, any question that you want to ask, if there are no questions, only then we'll proceed ahead. But if you have any query, any simple doubt, you can ask me right now because without uh, the prior knowledge, without the clarification with respect to whatever we have covered so far, the further topics will not be much understood to you. So if you have any query, any doubt, single doubt, you can get it clarified now so that we can proceed ahead with the subsequent topics. If you have any doubt, you can stop me anytime in between and you can ask. If there is no doubt, uh, we shall proceed with the base topic, that is the version space and the candidate elimination algorithm. So in the previous lecture, just a quick recap, we discussed about the Findes algorithm, its issues, its key properties. We discussed about the hypothesis space, the instance, taking the same example of the enjoy sport, and then we discussed about the general to specific ordering of hypothesis. That was nothing but the concept learning, right? So with respect to the same, taking forward the same understanding, we are now going to discuss about what is a version space and candidate elimination algorithm and how version space is used or how we can form a version space in the candidate elimination algorithm. So before going into candidate elimination algorithm, there are a few basic things that we need to understand, few fundamentals to be understood, like what is version space, how it is represented, uh, what are simple algorithms that we will discuss the algorithm, the list then eliminate algorithm, which gives us idea how version space uh, can be used or can be formed, right? So before going into what is a version space, the I would like to give you a brief overview of what we discussed, that is the Findes algorithm and the candidate elimination algorithm. Right. So candidate elimination algorithm is just another approach, like Findes algorithm. Findes algorithm was the first algorithm or the first approach that we learned for the concept learning as a search, right? So candidate elimination algorithm is another approach to the concept learning. Uh, and the main difference, the main idea of candidate elimination, how the candidate elimination algorithm is different from Findes algorithm is, if you can recall in the Findes algorithm, the main property, the key property of the Findes algorithm was that it guaranteed us to give at least one hypothesis. That is, it guarantees us to output at least one hypothesis which satisfied by the constraints, right? So in the candidate elimination algorithm, the main idea, the key property here is to output a description of set of all hypotheses, right? So the candidate elimination algorithm, it gives us a set of all hypotheses which are consistent with the training example. Unlike the Findes algorithm gives us the uh, at least one, only one hypothesis, right? It guaranteed us one output which was the hypothesis. But the candidate elimination algorithm gives us the set of all hypotheses which are consistent with the training example. So as the name suggests, it is candidate elimination. So what we do is we select few candidates and we then eliminate to find a right fit. So we'll discuss about these things later in the later section. But before that, there are few definitions, there are few basic concepts uh, which have to be learned to understand this algorithm. Right. So version space is the concept which the candidate elimination algorithm makes use of. But like I said, the Candidate elimination algorithm is the second approach. The first concept, the first algorithm that we learned was the Findeis algorithm. And I told you how is it different, how Findeis algorithm is different from candidate elimination algorithm. So basic difference is Findeis gives us only a specific hypothesis which is consistent with the, which satisfied the training examples, whereas the candidate elimination algorithm gives us the set of all hypotheses, right? And how we do it? How do we get that? We get that by using a more general than partial ordering, which we already discussed in a previous lecture, right? What is more general than? Then we discussed about what is more general than or equal to partial ordering. So we are going to make use of more general than partial ordering. So by using this more general than relationship or more general than partial ordering, we are going to uh, execute this candidate elimination algorithm. Now, the candidate elimination algorithm as well as the Findeis algorithm, they both are the concept learning algorithms, right? But the major difference is I mean, in both the cases, that is, when we talk about the practical application of the candidate elimination algorithm as well as the Findeis algorithm, the they are limited. They are limited by the fact that they both perform, you can say poor, they perform very poor when given a noisy data. Or let's say, I hope you all know what is a noisy data, right? A noisy data can be considered which is not relevant to the training example, which is not related to the constraint or uh, the concept which we are making use of to learn the to make the model learn, right? So when we have that, we can say irrelevant data, we can consider it as a noisy data. So this is a drawback, you can say, that the candidate elimination algorithm as well as the Findeis algorithm, they both somewhat doesn't perform very well or perform very poor when we have these noisy data in our training set, right? So, but most importantly, this the candidate elimination algorithm. The reason why we still use this candidate elimination algorithm, despite the fact that it doesn't give us very good result when we have a noisy data, the main reason why we use it, it provides a useful conceptual framework, right? It gives us a useful conceptual, a basic fundamental conceptual framework for introducing us several fundamental issues, right? Fundamental issues in the machine learning. So, though it might not have a very wide range of applications, I'm talking about the candidate elimination algorithm, though it might not have the wide applications, you can say, but the reason why we still use is it gives us the fundamental, it gives us the fundamental framework to address these several issues of this machine learning. These are the fundamental issues of the machine learning. So I hope this is clear why we still use candidate elimination algorithm despite it has a few limitations. Right. So talking about the application, as mentioned by the author, he has mentioned the application which he has worked upon, the Tom Michel. He has worked upon the chemical mass spectroscopy, which was implemented using the candidate elimination algorithm in 1979. And in 1983, again, the candidate elimination algorithm was used in a heuristic search algorithm, right? Heuristic search uh, application. So these were the two applications wherein the author has made use of the candidate elimination algorithm. Other than that, there are few more applications, but as I said, there are limitations with respect to candidate elimination algorithm application. The reason being it doesn't perform better or up to the mark when we have a noisy data in our training set or a training data set, right? So having said that, let us go on and understand how can we represent a version space, right? In what forms can we represent a version space and what is a version space? So before that, if you can recall, we discussed about the consistency. What is a consistent data, or how can we say that a hypothesis is a consistent hypothesis? Then we discuss about how or when a hypothesis can be said to be a satisfied the constraint. right? So talking about that, the let us understand what is this consistency and what is this uh, parameter of satisfaction what hypothesis has to achieve, right? So the simple definition of consistent is that a hypothesis h, small h denotes, as you can recall by now, that h is a particular hypothesis. Small h, lowercase h, denotes a particular hypothesis in a set of hypothesis capital H. So a hypothesis H is consistent when a set of training examples D, capital D, a hypothesis H is consistent with the set of training examples if and only if H of X is equal to C of X, right? H of X, that is hypothesis for the instance X, is equal to the training concept C of that instance X, right? For each example X, C of X in the D, that is X is the instance and C of X is the target concept of that instance X in the training example set of training examples capital D, right? So this can be denoted by using this formula, that consistent H comma D is, you can say, is equivalent to or is belongs to, or you can say this is also known as that it is a set of, consistent H of D is a set of, or you can say it is equivalent to, for all X comma C of X, which are element of the training data set D, such that the H of X is equal to C of X. Now, if you can recall that, having said that, that this is the definition of the consistency, how we, when we say that hypothesis is consistent to the training data set, we can say that h of x, when the h of x is equal to c of x. Now, let me go back and show you. We discussed about when a hypothesis is satisfy a particular constraint. But if you can recall that when h of x is actually equal to 1, then we can say that it was satisfied. So let me show you quickly. Uh, I think, yeah, here. So here we discuss about how, yeah, in the more general than relationship, we learn that hypothesis H, in capital H, we say that instance X satisfies hypothesis H if and only if H of X is equal to 1, right? So this is one major difference that you have to note, that a hypothesis is said to be satisfied when H of X is equal to 1. But a hypothesis is said to be consistent when we have H of X is equal to C of X. Right, so let me go back quickly to my current slide. Yeah, so as I said, we can say that a hypothesis is consistent only when h of x is equal to c of x, right? So h of x is the hypothesis for the instance x should be equal to the target concept c of that instance x, right? So having learned about what is consistent and what is satisfies, or how a hypothesis is said to be consistent and when an hypothesis is said to be satisfied. Now we can see you can see here that the candidate elimination algorithm represents the set of all hypotheses, as I mentioned in the previous slide. That major difference of candidate elimination algorithm and finder's algorithm is that the candidate elimination algorithm gives us set of all the hypotheses which are consistent with the, please note the difference here, consistent and not satisfied the constraint. It is consistent with the observed training examples, which is nothing but capital D. Right? So now the question, what is version space? So this subset, this set of all hypotheses, what the candidate elimination algorithms gives us in the form of output, this subset is called as a version space. Right? This subset of all the hypotheses that the candidate elimination algorithm is giving us as the output is called as the version space. Now, to make you understand, just to give you a brief view of how a version space uh, can be defined, let's say this is the definition. You can say that the version space, which is denoted by VSHD, that is version space for the with respect to hypothesis H, uh, and the training example D is the subset of hypothesis. Right? So I think the thing is clear that what is version space? It is the subset of hypothesis from the H consistent with the training example D. Right? So underline this main concept, that is it is consistent and not satisfied the training example. So here is how we can denote uh, version space, right? So version space Vs h comma d is equal to, or you can say it's a subset. You can also define this as a subset or belongs to this three dash line, three equal to sign. You can call it as either it is equal to, equivalent to, or it belongs to, or you can say it is a subset. Right? So they all means the same. Version space H comma D is subset to or equivalent to, you can say, H element of capital H, and such that uh, consistent H comma D, right? It is consistent. The hypothesis is consistent with the training example D. So I hope the definition of virgin space, the difference between the finite algorithm, the candidate elimination algorithm, as well as the difference between the uh, how a hypothesis can be called as a satisfying the condition, or when an hypothesis can be called as a consistent with the training example. I think so far the thing is clear. Or any doubt, please you can stop me and ask me anytime. Let me know if you have any doubt. I'm going very slow. I'm repeating the things every now and then so that the uh, concept is clear and it's totally understood. But if you still have any doubt, you let me know. You can stop me anytime. If you have any doubt, you let me know now before proceeding. Yeah, you can unmute your mic or you can put it in the chat box, please. If you don't tell me whether the things are understood, I will not know whether I should proceed or not.
मजा पडते
Yeah, tell me if you have any doubt. I'm waiting for you guys. I hope the difference so far is clear. What is a finite algorithm? How is it different from the how candidate elimination algorithm is different from finite algorithm? What is the difference between hypothesis getting satisfied by the condition or hypothesis being consistent with the training example? What is a virgin space? Please let me know before I ask anyone. You can voluntarily, anyone can tell me whether the things are understood or not. Okay, Omkar Deshnur. Omkar Deshnur. Am I audible first of all? Can anybody acknowledge? Am I audible?
Yes, sir.
Okay, so may I know the answer whether the things are clear or we should proceed or should I repeat it once again? Sonali.
We can proceed, sir.
Okay. Anybody else who have any kind of doubt, please let me know. Or if you're fear of uh, unmuting your mic and telling me, you can put it in the chat box. No problem. Ketan says no doubt, sir. Okay. But I'm hearing from the same guys that those who are attentive. But what about the others? I don't know whether you are paying attention or no. But let me tell you, if the things are not clear now, the further things will be a little complicated. So if you have any kind of doubt, please you can stop me anytime and ask me so that I'll repeat it once again and we'll proceed only when we have the things crystal clear. Muhammad Arif says virgin space, sir. Repeat it once again. Okay, fine. So I'll once again repeat what is virgin space. Anything else? Any other doubt? Omkar Deshnur, Ravi says no doubt. Okay, that's what I am hearing from the same guys that those who are paying attention, but I'm not quite sure about others whether they are attentive, uh, are in doubt, don't want to ask doubt, or they are clear with the things. Omkar Deshnur is, I think, has left the mobile and gone somewhere out. Anyways, so let's focus and not waste the time of the guys who are paying attention. Uh, Answering your question, Mohammad Arif, that version space, right? So, as I defined in this slide, what does the version space? What do we mean by the version spaces? Was first to understand what is version space, we have to understand what does finders algorithm give us and what does candidate elimination algorithm give us, right? So, as we discussed in our previous lecture, the finders algorithm outputs us only one hypothesis, right? It guaranteed us the it guaranteed us that there will be at least one hypothesis which will satisfy our all the condition and at least one hypothesis which will be called as a output, right? But in candidate elimination algorithm, what the candidate elimination algorithm does is it gives us set of all hypotheses. Is it gives us all the possible hypotheses which are consistent with the training data set. So what is our training example? The training example, the set of training example, which is denoted by D, right? So what is these training example? If we can recall the table, if you remember the enjoy sport table, we had four example in that. We had three positive examples and one negative example. So those four example can be called as a observed training examples, right? So this is nothing, that is nothing but our capital D, right? That is our capital D, which is set of training examples. Now, among all these set of training examples, the candidate elimination algorithms gives us or outputs us set of all the hypotheses. Right? I already told you what is an hypothesis, right? So it gives us all the set of hypotheses. Now, what set of hypotheses? The set of hypotheses which are consistent with these observed training example. Now, next question is how can we say that, or what, when can we say that it is consistent? We say that it is consistent when we say that the hypothesis is consistent with this particular training data set or training example, if and only if the hypothesis for the instance x is equal to the training concept c of x, right? When it is equal to training concept. That is, h of x is equal to c of x. Now, when h of x is equal to c of x, for each of the instances x, target concept C of x in the training example set D, right? And which is exactly the definition, the above definition can be represented by this expression. You can say that consistent, we can say that hypothesis is consistent with the training example D when it is set, when it is, you can say it is equivalent to for all the instances X and training concept C of X belongs to the training example set D when h of x is equal to c of x. So this is the definition of consistency. So I hope so far it is clear that the candidate elimination algorithms gives us set of hypotheses which are consistent. Now these set of all the hypotheses, this set is what is called a version space, right? This set is actually nothing but a subset of all the hypotheses, right? So the collection of all the hypotheses that we have, candidate elimination algorithm is giving us a few hypotheses as the output. It's a subset. Now this subset is what we call it as a version space. Now to give you a little more understanding, and this is the definition of version space, right? So the version space denoted by VSHD with respect to hypothesis space H and training example D is a subset of the hypothesis from the H, which is consistent with the training example D. So I hope this is simple enough to understand, and this is the expression for the same definition what we saw. Right now, just to give you another understanding, let us understand by this diagram. So I have one diagram made for you that let's say we have a point wherein we have a most specific hypothesis which is denoted by phi, as we have already discussed in the previous lecture, and in the downside we have a most general hypothesis which is denoted by symbol question mark, which denotes any value is accepted, right? Question mark means any value is accepted, and phi symbol means no value is accepted. So when we say no value is accepted, it is very specific, right? We are not allowing any value, very specific. And when we say any value is accepted, it is most general, right? It is the most general hypothesis that we can possibly have. Now, let's say we have few set of hypotheses here, which are general hypotheses, and we have few set of hypotheses here, which are specific hypothesis. Now there will be one point wherein will have a maximally specific member of the from the set of all hypotheses, and also at the same time we'll have a maximally general member of the hypothesis from the set of hypotheses. Now this maximally general is denoted here with capital G, and maximally specific is denoted here with capital S. This point, the red dot point, right? Now, the in between hypothesis, what all the hypotheses we have in between these maximally specific members and maximally general members is what we can call it as a version space. Now, this whole set you can say is we can call it as a version space. I hope the definition of version space or what is version space is clear to you. Arif? Clear. Okay. Fine. So moving ahead, now once we have defined version space, so this is how a version space will look like when we talk about our previous example, that was our enjoy sport. So don't worry about what is this. I mean, how are we getting these things here? The only thing that we you have to remember at this point in time is that we have a maximally specific hypothesis here, right? And we have a maximally general hypothesis here, right? So we have actually two hypotheses here, one hypothesis here, that makes three. We have three more hypotheses here. That means we have total of six hypotheses in total, which are you can say suggested by the candidate elimination algorithm, right? But these three hypotheses, what we have here, these three hypotheses are our version space. This three hypothesis is a version space. This is our maximally specific hypothesis. Let me point a laser. Yeah. So this is our maximally specific hypothesis. The down below is our maximally general hypothesis, and the in between these three hypotheses which are generated by the candidate elimination algorithm is our version space. Now, please understand that these arrows, the arrows which are pointed, they denote that the direction in which they are pointing, that means the hypothesis is more general to the this hypothesis. Let's say, for example, yeah, let's say this first arrow. So this hypothesis, the G, which is sunny question mark followed by again a second hypothesis, warm question mark. So this hypothesis is more general than this hypothesis. So that is how we read the arrows here, right? So this hypothesis, let me point a laser. Yeah, this hypothesis is more general than this hypothesis. As you can clearly see, let's say, let's take this instance, this hypothesis. Sunny question mark question mark question mark question mark question mark. So we have first attribute value as Sunny, and all the values of others five attributes are followed by a question mark, which means any value is accepted. But when we see this hypothesis, we have first value as Sunny, which is exactly equal to this hypothesis, but followed by two question mark, which is again equal to this hypothesis general. But the fourth attribute value is strong. So we are specifying a value of this attribute here. That means this hypothesis is can be called as a less general, right, or a more specific than this hypothesis. So that's what the arrow means here. The arrow denotes that this hypothesis is more general than this hypothesis. And similarly, this hypothesis is more general than this hypothesis. The reason I think you can clearly make it out by now that we have three specific values in this hypothesis, whereas in this hypothesis we have only two specific values. So this is more general than this hypothesis. So, having said that, let us now understand how this output, how do we get this output, right? I first showed you the output so that you can relate what is a version space, what is, I mean, what form, in what form we will be able to get the output, so what an output will look like, right? So that's why I've showed you this, but let us break down this problem and understand. Maybe I think in today's class it might not be possible because we have less time to discuss this, but let's have a simpler example of how this candidate elimination algorithm, or how this virgin space, not candidate elimination algorithm, how a virgin space can be formed. So because unless you are clear with what a virgin space is and how we get this virgin space, we might not understand the candidate elimination algorithm. The reason being, candidate elimination algorithm makes use of virgin space, right? So let us understand with a simple algorithm, not jump on to candidate elimination algorithm. We will understand a simpler version of it, which is called as a list then eliminate algorithm, right? List then eliminate algorithm. So as the name suggests, we the set of hypotheses first, and then we eliminate one by one, so that we have a ultimately we have a list of hypotheses which are in the virgin space. So the list then algorithm, what it does, it takes the uh, it it assigns all the hypotheses, the list of every hypothesis, right? A list containing every hypothesis in capital H. Capital H denotes list of all the hypotheses. So it assigns this list to the virgin space. Now, for each training example, now we start a loop. We start a for loop that for we check for each of the training example that for each training example instance X and the training concept C of X, remove from virgin space the hypothesis which is not consistent, right? I already told you the definition of consistency, right? We call a hypothesis as consistent when we have h of x is equal to c of x. But let's say we have a training example which is not consistent, that is h of x is not equal to c of x. Then we remove that hypothesis from the virgin space. So we keep on doing this, we repeat these steps, we keep on removing the hypotheses which are not consistent or inconsistent, and ultimately we end up having a set of hypotheses which can be given as the output, and which is nothing but our virgin space, right? So once the loop is terminated, we have the output of the all the list of the hypotheses. Now this list can contain at least one hypothesis, or it can contain a few more set of hypotheses, right? List can have one or more than one hypothesis in the virgin space. That depends on what type of training example that we are going to provide. So this is a simple example of a simple version of, you can say, a candidate elimination algorithm, wherein we are first listing all the hypotheses and then we are eliminating those hypotheses. Right. So I hope this list then eliminate algorithm is clear. It's very simple actually. Now, the very important factor to remember here is the find S algorithm, as I discussed keep on repeating this thing, like the output that we get from the finders algorithm is that we have only one hypothesis. So if you can recall from our previous lecture we discussed in previous week, the finders algorithm was giving us only one output, which was only one hypothesis, right? Which was this, right? H is equal to sunny, warm, question mark, strong, question mark, question mark. So this was the output that we got when we executed our find dash algorithm. So you can revisit that lecture and you can see how we end up having this hypothesis as a uh, output for the find dash algorithm. So this was the only hypothesis which was given by the find dash algorithm. But this is just one hypothesis. This is just one of the six different hypotheses. Now, what is this six? Where is this six coming from? This six is these these six hypotheses, right? So we have one maximally specific hypothesis, two maximally generally hypothesis, and then we have three more hypotheses in our version space. So that makes us total of six hypotheses that we have. But in our finders algorithm was only able to give us one hypothesis as the output, which was this hypothesis. Right? So this is just one of the six different hypotheses from the set of hypothesis H that are consistent with these training examples. So I hope the difference is so far very clear. Moving ahead, now like I told you, I discussed with this with respect to this. This is just the output that we get at the end. Now to break this example and let's break this example and understand is this maximally specific, what is this maximally general hypothesis, and what is the definition of these maximally general and maximally specific. Right? So these are called boundaries. Right? Let me go back to the working space diagram which I showed you. The Yes, so these is what you can call it as boundaries, right? This is a maximally specific boundary and this is a maximally generic boundary. Now, how do we set this boundary or when do we decide that when we reach this level of maximally general hypothesis, we call it as a boundary. When do we understand that this is the boundary of a maximally specific hypothesis or a maximally generally hypothesis? So the boundary, this let's say general boundary, we can define this general boundary with respect to the hypothesis space H and the training example D, that it is a set of maximally generally hypothesis of H consistent with the D. And when we call it as a this is a boundary when we satisfy this condition, right? Which is G, capital G, is equivalent to, or you can say is subset to the small g, which belongs to the set of hypothesis H, such that it is consistent with the training example D, and at the same time it does not belongs to G dash. Now what is this G dash? G dash which belongs to the set of hypothesis G, and what is this G dash? G dash is the set of hypotheses that we have which are more general than our existing set of hypotheses G, right? So G is our existing set of hypotheses which are maximally general, but G dash is those hypotheses or those set of hypotheses which are more general than these set of hypotheses, right? So we have three conditions to be satisfied in order to define this boundary. These are the three different conditions, right? First of all, the G has to belong to the set of hypothesis H, which in such that is consistent to training example D, and it does not belong to G dash. It shouldn't belong to G dash, which is again a set of an element of a set of hypothesis H, and G dash is more general than G. The third constraint is that the third condition is that it should be the G dash should be consistent with the training example D. So when we have this all three conditions, then we can say that it is said to be a general boundary G, right? Similarly, for specific boundary, for the specific boundary capital S with respect to the hypothesis H and the training set D, it is set, it is the set of minimally general, right? In other words, it is maximally specific. When we say it is minimally general, it is nothing but maximally specific, right? So please understand here, the general boundary is when we have maximally general member, and specific boundary is when we have minimally general member or maximally specific member. They both mean the same, right? When we have these members consistent with the training example D, and this is the expression for this condition. Now again, we have three conditions here, which all three of them have to be satisfied in order to call it as a specific boundary S. Right? So specific boundary S is equivalent to, you can say, or is subset to small s element of set of hypothesis H, such that it is consistent to the training example T, and it does not exist in S dash, which is element of H, capital H, and small letter s is more general than. Now please understand the difference here. Here we are saying that S is more general than S dash, whereas in the general boundary definition we discussed that G dash is more general than G, right? So the reason is here we are defining the more general than relationship. That's why G dash is more general than G, but here we are defining with respect to specific. So specific is set of specific S is more general than S dash. That's why first we are having S here and then S dash here, whereas in the previous case we have G dash here more general than just G. And the third constraint, the third condition is it should be consistent with the S dash. With it, the S dash should be consistent with the set of training examples D. So this is how we set a general boundary G and a specific boundary S in our virgin space, right? So hopefully you can recall this, what we discussed, this boundary, these boundaries, what we call it S for maximally specific member, and G is the maximally general member. So I hope the thing is clear. When we set a general boundary, when we set a specific boundary, and when we define both of these boundaries, S and G, this S and G, only then we can define what is a virgin space, right? So let me come to the back, the diagram. Yes. So when we define these boundaries, this S boundary and the G boundary, only then we can define this whole virgin space, right? Unless we have a set boundary for it, we cannot call uh, what type of hypothesis will fall into this virgin space. So virgin space can be defined when we have this S boundary and G boundary, and how we do define it? That virgin space for the hypothesis, set of hypothesis H and the training example D is equal to a hypothesis which belongs to H such that it exists in S, small s, wherein this S belongs to this capital S specific member, and it exists in G, the G exists, it belongs to the general boundary G, and G is more general than H, and H is more general than S. So G is the most general, S is the most specific, and our hypothesis lies somewhat in between these boundaries. Then we can call it as a virgin space, right? So I hope the things are clear. What is virgin space? So candidate elimination algorithm, we will take it in our next lecture, because we will discuss the algorithm, and at the same time we will have a example of how we end up having these, yes, these hypothesis as our output, right? So in our next lecture we will split out this stepwise execution of these hypotheses. How do we get it, right? So so far clear, or any doubt with respect to anything you can ask me? Is everything clear? Okay, Ravi says clear. Good. Anybody having any doubt? Okay, if you don't have any doubt, you can we can conclude the lecture here and we can leave the meeting. Thank you.